Hello everyone and welcome back to our CSIR NET problem solving series on Fractal Frontier Maths. In the previous video, we discussed the CSIR NET June 2013 problem where we derived a general solution of the initial value problem of the type dy by dx equal to k y raised to the power alpha, where alpha belongs to 0 to 1 subject to the condition ya equal to 0. That solution forms the foundation for today's discussion because the CSIR NET June 2040 problem directly builds upon it. So if you haven't watched that video, I strongly recommend checking it first. The link is in the description. Let's recap the previous problem. This is the initial value problem subject to the condition y equal to 0. It has multiple solution, infinitely many solution. First solution is yx equal to 0, which is a trivial solution. Second solution is yx equal to beta dash x minus a raised to the power gamma, where beta dash and gamma are constant which are derived by the separation of variable method. And based on this solution, we derived infinitely many solutions of the type this, where c is a constant greater than equal to a. In today's discussion, we will use that solution to answer this question. The problem is, let ut be a continuously differentiable function taking non-negative values for t greater than 0. The value of t is greater than 0 and satisfy the differential equation u dash t equal to 3 ut raised to the power 2 by 3, and the initial condition is u0 equal to 0. Which of the following are possible solutions of the above equation? So we have to choose all the correct solutions. So let's begin. So similar to the previous problem, we first derive a solution by the method of separation of variable. So this is the given differential equation. We can write it as du by dt equal to 3 u raised to the power 2 by 3. Now separate the variable u and t. We will get du by 3 u raised to the power 2 by 3 equal to dt. On integration, it will be integration equal to t plus a, where a is a constant which will be determined by the given initial condition. On integration, we will get this, and so u raised to the power 1 by 3 equal to t plus a. It is given that at t equal to 0, u equal to 0. Therefore, a must be 0. We will get u raised to the power 1 by 3 equal to t. So ut will be t raised to the power 3. So we can see that ut equal to 0, which is a trivial solution because it satisfies both the differential equation and initial condition. Ut equal to t cube, which we have derived by using the method of separation of variable. So in general, for c greater than equal to 0, uct equal to 0 when t is less than c and t minus c raised to the power 3. We have used this solution to generalize this in the form of t minus c raised to the power 3. So this will be a solution to the given initial value problem. So if we see the given problem, here c is 1 and c is 3. So we can put first c equal to 1, which is greater than 0. So for c equal to 1, when t is in between 0 and 1, the solution is 0. When t greater than equal to 1, solution will be t minus 1 raised to the power 3, which is a solution to the given initial value problem. Similarly, if we take c equal to 3, then ut equal to this, which is also a solution. Hence, all the four options are correct. So now we will see a similar problem. So there is another problem which is asked in December 2015 paper. It is given that ut, a continuously differentiable function taking non-negative values for t greater than 0 and satisfying the initial value problem u dash t equal to 4 u raised to the power 3 by 4 with the condition u0 equal to 0. Then we have to check what can be the possible values of solution ut. So here ut equal to 0 will be trivial solution. If we calculate it, the solution du by dt equal to 4 u raised to the power 3 by 4 by the method of separation of variable. Let's see what will be the solution. So on integration it will be a is constant, it will be u raised to the power 1 by 4 equal to t plus a. If we put u0 equal to 0, then we will get equal to 0. So u raised to the power 1 by 4 equal to t, or we can see that ut will be t raised to the power 4. So by inspecting the options, ut equal to 0 will be the trivial solution, ut equal to t raised to the power 4, which is a solution by the method of separation of variable, and we can extend this solution for any c greater than equal to 0 by branching it out for t 0 to c and t minus c raised to the power 4 t greater than equal to c. If we put c equal to 1, we will get third option. If we put c equal to 10, we will get fourth option, and all the four options are correct. So these are some very easy problem asked in multiple selective questions of 4.75 marks. So by using this method, we can obtain general solution y is equal to this. We just have to keep in mind this kind of equation, dy by dx equal to k y raised to the power alpha, where alpha is in between 0 and 1, where condition is given y equal to 0, where a is any real constant. So it will have multiple solutions. One is trivial solution yx equal to 0. One we will get by using the method of separation of variable, and by this solution we can extend this solution by replacing this a to any constant c, where c is greater than a. Okay, here in the today's problem a is 0, so we just get solution like x minus 0 raised to the power gamma. We replace it by x minus c raised to the power gamma. In next video we will discuss the interval of existence by using Picard's theorem.